Welcome. I want to talk to you about penalty alternating direction methods for mixed integer optimal control with combinatorial constraints. My name is Lars Schewe, and I'm presenting the work that I've done together with Simone Göttlich, Falk Hante, and Andreas Potschka. So, what are these words that I all mentioned in the title? So we are talking about mixed integer optimal control. So we have a classical optimal control problem, but with integer variables typically over time. So at each time step t, we can take a decision to switch something on or off, or to switch gears if we're thinking about cars. And we have an optimal control problem. So essentially we have a problem where the dynamics of the system are given by an ordinary or partial differential equation. We have combinatorial constraints, and very specifically what I mean by that is that we have integer decisions that actually couple over time. So you could think, for instance, about having the integer variables interact with each other at each different time step, so that if something is switched on, you have to switch something off or something like that. But what we are interested in specifically is integer variables that couple different time points. So things where if you do something at time t, you have to do something else at time t plus k. So that is something which occurs quite often, say for instance minimum dwell times. So it has to stay on for a certain time, or it has to stay off for a certain time, things like that. And people have looked at this for specifically minimum dwell times. You can look at a paper by Zeiler and co-authors where they looked at special methods for this specific case because it's so important. We're looking at a more general thing here, general constraints that couple over time, even though most of our examples or all of our examples will be minimum dwell time examples. And the final ingredient is the method that we're using, which are penalty alternating direction methods. It's a class of heuristics that was introduced by Geisler and co-authors and is closely related to feasibility pumps. So you can even think of it as sort of a framework in which you can explain feasibility pumps. So that means that what I'm talking about here, you could view it as a sort of feasibility pump for specific mixed integer optimal control problems. We cannot use penalty alternating direction methods as introduced in the paper. We need to do some slight tweaks to make them work for the specific computational examples, because we cannot guarantee optimality because we have to discretize everything, so everything is only epsilon optimal. We've discussed this in the paper. I will skip over that part and essentially only talk about sort of the version without epsilon optimality to not introduce technical complications. I want to mention that these combinatorial constraints are important for modeling, but not for theory. And I want to be very clear, they are also important for the theory. If you look at this very classical example by Fuller, which is a classical optimal control problem, even not a mixed integer optimal control problem, if you solve this, what you will see is that you get a solution that is mixed integer, so u will always be plus or minus 1. You find optimal solutions with that property. But the solution switches infinitely often between plus and minus 1. So this is something that you cannot have in practice, where you have sort of, which is why it's called chattering control, where you have to essentially switch on and off infinitely often in finite time. So this problem doesn't have a solution from a theoretical perspective if you don't allow switching infinitely often, or if you don't introduce additional constraints. And this is the standpoint that we are taking. We need, in our case, dwell time constraints to make sure that this has what we call the uniform finiteness property, so that you have finitely many switching time points over every interval. This is the general problem we are looking at. It has a specific structure from which you can generalize a lot of things with standard techniques from optimal control, but this is the way that is easiest for us to look at. So you have an objective function that only looks at the value of the state at the end time point, capital T. You have a system of differential equations that couples the state to both the continuous control U and the integer control V, and has a linear part, which is given by this matrix, or by this operator to be precise, A, and by this nonlinear function f. The setting is chosen in a general setting so that we can easily adapt it also for partial differential equations. If you want to keep everything simple for you, assume that all these Banach spaces are finite dimensional. So you have a continuous control, as I said, which has continuous control constraints. You have combinatorial control constraints, which are the ones that are interesting to us. And you have the state y. How can you solve this? So you can discretize everything, sort of make the spaces, all spaces that are occurring here, finite dimensional, then discretizing in time, and then you get a very large mixed integer nonlinear programming problem, and you can solve it with all the techniques that are discussed here in the conference or that you know of. However, these become very large and you get lots of discretization dependencies. So depending on how you discretize, the solution might change a little bit, and you have to be very careful that all your discretizations fit together. And more often you have the problem that you cannot adapt your discretization. So even though you know that over a certain amount of time nothing major happens, you still have to discretize everything because otherwise your model might not fit. This is the drawback. Essentially, your mixed integer nonlinear problems become too big. What people have been studying is how to use the very good techniques from classical optimal control to build on that. So one idea is to convexify the problem with a technique called partial outer convexification, and then solve an approximation problem to sort of fix the non-integral controls to become integral controls. And if you don't have combinatorial constraints, then this is easy. You can do a technique called sum-up rounding. If you have combinatorial constraints, this is hard in general, and there have been lots of work to sort of get this working and studying the problems and deriving ad hoc techniques to solve these problems. And this is in general very difficult, which is why we want to use heuristics here at this stage. So what do? We combine and leave partial outer convexification. This is our working horse. But we use a split of the problem into two parts to then glue them back together with an alternating direction method, or our penalty alternating direction method. So we split it into two parts, the mixed integer optimal control problem without the combinatorial constraints, and then a mixed integer problem with the combinatorial constraints, and then we glue this together using penalty ADM. Let me give you a rough overview over the alternating direction methods and the penalty version of that. So the idea is you have an optimization problem that is split into two blocks. The variables are split into two blocks, and the functions couple them. So you have objective functions that couple them, and then you have some constraints that both involve x and y, but you have also constraints that only involve x's and only y's. And what you do classically is just you choose some initial values, and then you fix one component, say the y's, and optimize only in the x direction. Take the new value, fix that, and then optimize in the y direction and alternate between those two. Obviously, sometimes this works, but in many cases, it only gives you something weaker. And the notion that essentially means that the alternating direction method has gotten stuck is what is called a partial minimum. And you can show that these methods essentially always get stuck in a partial minimum, or at least converge to a partial minimum. So this is a very weak notion, but note that if you have something like a continuously differentiable function, so f is both in continuously differentiable in all variables combined, then you will get something that is a local minimum, for instance, and all the constraints as well. Or if it's convex, you even converge to global minima. So the obvious question is, how do we deal with these constraints? that couple x and y. And the idea that we proposed in the older paper for finite dimensional questions was to essentially use a penalty method. So lift all the complications into the objective function using penalty parameters, and then alternate. And if you get stuck, if your alternation loop gets stuck, just adjust penalty parameters. So the penalty method that we are using is essentially we start again with some xy pair and penalty parameters, and essentially have the loop that we, in the inner loop, use alternating direction methods to compute a partial minimum. And if we get stuck in a partial minimum, we adapt the penalty parameters to leave the partial minimum. And in our case, what this means is we introduce auxiliary variables v tilde, which are just a copy of the integral controls. So we have v as the original integral controls and v tilde as the new integral controls. And what we are doing is essentially we use the L1 norm of these two, of the difference of these two as our new constraint. So essentially we have the constraint v is equal to v tilde for all times. And what we are doing here is essentially saying we want to penalize deviation of that. So if we deviate from, if the integral controls deviate from each other, then we want to penalize this. But now this means we have a very clear decomposition of our variables into two blocks. We have all the old variables and we have the new v tilde variables as two different blocks. So if we fix the v tilde variables, we essentially get the old problem just with an additional term in the objective function. So we have our old optimal control problem, still a mixed integer optimal control problem, but with no combinatorial constraints. If we fix v and all the other things implicitly, what we see is the only term that is actually interesting is the integral term, so the deviation between v and v tilde. And because we put the combinatorial constraints only on v tilde, now we have a problem that after discretization is actually a mixed integer linear problem. We only need to get a v tilde that is feasible for the combinatorial constraints that approximates v as good as possible. So for the first subproblem, we have two alternatives. We can either convexify and sort of get rid of the integer constraints in the first subproblem, or we can leave the integer constraint in the first subproblem and get a proper solution just using sum-up rounding. And we tried both in the computational results. We have some theoretical results, which are pretty sort of, after some nasty technical assumptions, pretty sort of straightforward. So we have, if you have a global minimum of our original problem, where the original problem satisfies technical assumptions because we are infinite dimensional, then we can find a finite penalty parameter so that this whole thing is a partial minimum of the auxiliary problem for all larger penalty parameters, which is a type of exactness result. So we have an exactness result for this. On the other hand, if you have an infinite, if you drive our penalty parameter to infinity, then we get at least a partial minimum of a reasonably chosen feasibility measure of the whole thing. So even if you don't become feasible, which means that v star and v tilde star are not equal, you still get something that minimizes infeasibility in a reasonable sense. And for the details, I refer you to the paper. For the computations, we had two examples. I'm discussing the more theoretical example. We have a more practical example with PDEs in the paper, but I stick to the ODE example here for sort of ease of exposition. So this is a variant of the problem that we saw before, of Fuller's problem. you see that it has this term which minimizes the square of the first state, but it also has a term that minimizes the distance from 1/100, 0 in the 2 norm at time 1. So essentially we have a constraint that drives it to this point 1/100, 0 at time 1. But we don't have it as a constraint, we have it as penalized in the objective function. And then we have sort of Fuller's problem rescaled so that it's a binary control and not a ±1 control. And what you see is we have added a dwell time constraints that depends on this tau min. If you set tau min to 0, then you get the original problem because the constraint vanishes. Otherwise, what we say is that within an interval of length tau min, we don't want to switch more than once. And here you see some results for different tau min. So on the left is tau min is 0.04, on the right is 0.05. And you see the different methods. So one, as sort of reference implementation, we fully discretized the problem and solved an MIQP in this sense, because using the right discretization and everything stays quadratic. And so you get a mixed integer quadratic problem in this case. The other version was this combinatorial integral approximation as a second sort of reference. And then our two methods is either the alternating direction method without sum-up rounding, so just relaxing the integral controls in the first subproblem. And the other is solving it with additional rounding. And what you see is that if you do this, all solutions are relatively close, is with the slight exception of the alternating direction method for smaller tau min. But otherwise, they are reasonably close. The controls look reasonably similar. The states in this case are reasonably close. The states look reasonably close in what they compute. And you will see later in the objective functions that the objective functions are comparable. So what we see if we look at the objective functions, here lower is better, that for small tau, combinatorial integral approximation provides the better results, which is not necessarily surprising because the dwell time constraint is less important. So fixing the dwell time constraint from a sort of infeasible integral solution is not as difficult. Whereas for larger tau min, our methods get better. So you either have the sum-up rounding, or for the largest, even our alternating direction method without the sum-up rounding outperform the methods. And they are relative. You see some drastic distances to the MIQP solution. So the MIQP from the solution quality always outperforms the other methods. However, what you should see is that the runtimes of the MIQP solution are relatively long, and that the alternating direction methods always run in relatively short time, so that they could be very feasibly run as sort of a primal heuristic before you go, say, in an MIQP setting. As I said in the paper, we have a PDE examples, a network of electricity transmission lines using the telegraph equations, which is a system of PDE, system of hyperbolic PDE. The numerical results don't look too different. It's just to show that our framework is even adaptable to the PDE case. For that, I refer you to the paper. Here is the paper. I'd like to thank, first of all, my co-authors, and then all of you for listening. Thanks.